And so it's basically, 90% of customers can just get by with Designer. The other 10% want to have the Pro version. And then there's a small number of customers who want to be able to write their own modules as well. For the most part, you saw we have hundreds of modules, okay? And we typically have a module for what you want to do. Or you might be able to combine a few modules together and then create the desired functions you want. So it turns out there's a lot of pieces to a module, okay? And so there's a lot of stuff that needs to happen. And I like to split up kind of into two parts, okay? I call it the model description. This is kind of what MATLAB knows about and Designer knows about. And then there are the target files that'll run in real time, okay? So if you think about it, what does Designer need to know? Okay, Designer needs to know, where does this module appear in the module browser on the left-hand side? There's got to be a little bitmap for it, okay? When you drag the module out, it draws a line graphic that's using a SVG format. You right-click on the module, you say help, okay? So there's all these bits and pieces of information that you need to do for the module. What happens then in MATLAB is MATLAB also has a description of the module. So it knows what inputs and outputs it has. It knows all about the variables. Okay, what's the name of the variable? What's the data type? Is there range information? Okay, it knows how to draw the inspector. Do you want to use a knob or a slider? MATLAB has all the information. Okay, and there's quite a bit there. And we'll do some deep dives looking at some of the different source files there. Okay, and then what happens is there's also corresponding C code that gets executed. So each module is in its own .c file, and then we'll group a whole bunch of modules together in different libraries. Okay, so for each C file, there's also a corresponding header file, and in the C file, you'll see that there's a constructor function which does memory allocation. There's a processing function, bypass function, and then some control functions for get and set. And the server also needs to know all the variable information and data types and so forth. And it has something called the schema info, which is essentially like the header file in C, but in a text readable, in a readable form for the server. And so this is what we're using when we're running in native mode. We're executing within the server. And then when we switch to the embedded target, well, we have to have the same files here down on the target as well, running. Okay, so there's lots of little pieces here that are needed to build a module. So we'll go through and take a look at these pieces. Okay. Now what happens is on the PC, the modules are contained in these DLL files. So these are dynamic link libraries. So what happens is they're organizing these different module packs. And when the server launches, there's an AWE server.exe. When that launches, it basically looks for all the DLL files in the same directory that the server exists in. And then the server opens each of the DLL files, examines it, and says, hey, are there modules in here that I can use? And if so, it reads the information and imports all the information about those modules into the server. Okay. The module files, the DLLs, also contain the schema information. So the server can load the information, and then it knows that, hey, the scalar module has a variable called gain and its floating point. So it has all that information. Okay. So you can see all the available modules on the server by going to server and then target menu, list modules. So I can switch here to the server. And I'm connected on USB, target list modules, and it'll show you all the modules, and it'll tell you which corresponding DLL in the PC holds that module. Okay. So what happens as a result is, so the modules have to be on the DLLs for the server to know about it. So if I'm developing a module for the target here, that module also has to exist on the server. Okay, so you can't just develop it here and not on the server. There's got to be a form of the module that runs on the server too. Okay, So that's how things are organized on the into the DLLs. So here are the steps to making a new module. Is one, you start with MATLAB. You write a bunch of MATLAB code, okay, and you describe the pins and the variables and all that stuff. And then what you do is you write some C functions. And then when you have the C functions done, is you use MATLAB to generate a whole bunch of files. So MATLAB will generate the header file for you, for example. And MATLAB will generate the XML and the schema files and so forth. And we chose to do it this way to basically have MATLAB be the master repository, for example, of the variable information. And then it'll update the information in multiple files. Okay? Otherwise, it's easy for things to get out of sync. You know, if you add a new variable and you forget to add it in the XML file, then that's going to cause trouble. Okay, so we're going to see that there's a master model in MATLAB of all these things. So that's the first steps. So basically, start with MATLAB, you write some C functions, and then you have MATLAB generate these files. Next thing you do is you add the generated .c file to your project. You build a DLL. You test it out on the PC. So I would recommend you write a regression test. Make sure that it's working. Once it's working on the PC, you move it down to your embedded processor. So you basically add the modscaler.c to your project, to your executable project, put it into a library. Then you basically test on the target, make sure that it's working, and then you can profile, and after that you optimize the code. And then you can use our built-in profiling capabilities to essentially guide your optimization. So these are the steps to writing a module. So you start in MATLAB, it generates C code, and then you move into building the C code and so forth. So what this means is when you're writing a module, you need MATLAB, you need Visual Studio to build the DLL on the PC, and then you're going to need your target-specific files. So maybe you have Kyle or IAR on an embedded processor, maybe you're using GCC under Linux to build the modules. Okay. So let's take a look at a module. So this is scalar module. This is actually a deprecated module, but we use it as an example because it's really easy. So this is what the MATLAB code looks like. Okay. So this is standard MATLAB syntax. I don't know how many of you have programmed MATLAB, or it's been a long time ago, but basically I'm declaring a new function, and the first argument for a module function is always the name. Okay, what are you going to call this? You're going to call it left gain, right gain, volume, whatever. What we do next is we create a module object, and we give it a class name. So this is going to be a unique identifier for this module, and scalar is going to be used in the generated file name, it's going to be used in the XML file name, and so forth. So this is called the class name of the module. And then you give it a short description. What does this module do? Okay. Next you assign the name inside the data structure. Then you add variables to the module. And this module is just a simple multiplier. So there's a single variable called gain. You can see it's a floating point data type. It has a default value of 1. How is this variable used? Is it a parameter that's settable by the user? Is it a derived variable, which means, for example, maybe it's a filter coefficient which is computed based on other parameters. Maybe it's a state variable that's updated by the processing function, and so forth. Just short description, what does this variable do? You can optionally set range information. So this is the default range. I want to go between -10 and +10. There's some units information for when you draw the inspector. Okay. Next thing I'm going to do is I'm going to add an input pin and an output pin to the system. Okay. And this pin type function returns an object, which is the basically the range information for this pin. And what it basically allows me to do is put constraints on how many input channels, what's the block size, and so forth. And you can see there's 5 arguments here, and a bunch of them are empty. I put an empty matrix there. An empty matrix means there's no constraints placed on it. This module can do any number of channels, any block size, any sample rate. It only supports floating point data, and it can do real or complex data. Okay. So those are the kind of constraints you can put on the pins. Okay, you add the pin, you name it. What you do now is you basically tell MATLAB, you say, hey, I'm going to use the following file, innerscalarprocess.c. So that's the C code that I hand wrote. We'll look at that in a minute. So that does the processing function for this module. Okay. Wire allocation across. That means I can use the same input-output buffers from pin 1 on the input side to pin 2. So it can reuse wire information there. If I say distinct, then it's always going to give me a unique output wire. Okay. Some C also information for help. I'm going to attach a slider to the gain variable, and now you can see the range is plus or minus 10. So that defines the inspector. And a bunch of browser information. It's going to go into the folder called gains. I specify the bitmap file. Search tags, so if I search for scalar, it gets found. If I search for volume, it gets found. What shape do I want to use? So you can either define a custom SVG, or you can just use some of our basic shapes. Okay. So based on that information that we gave it, when I generate the files, MATLAB is going to generate the following header file. Okay? And I'm going to start out here that this is essentially the instance descriptor for the scalar module. Okay? And what it is it's essentially, it has a common header called instance here. That's a common header shared by all the modules. And after that, it has the module-specific variables. And you can see that, hey, this is exactly what we told it. We said, hey, there's a floating point variable called gain, and here's a short description of it. So this is kind of all auto-generated for us. And if we had more variables in here, you would see the variables and so forth. Okay. So we have some limitations on the variables. So the variables have to be 32-bit quantities. So you can have float, int, fract. And then you can also have pointers to arrays of data and so forth. So this is the instance structure that gets generated. Okay. What also happens is we also write some other stuff. Is we generate an object ID for this module, and I'll show you where that comes from. So what happens is down on the target, this module has an object ID of 2039. So we can essentially find this module down on the target based on its object ID. And then finally, there's also some offset information. So the gain variable is an offset of 8 words from the start of the structure. So this header is actually 8 words big. Okay, so this offset information is going to be needed later if you want to read and write the variables through the tuning interface. Okay. So inside this instance descriptor is basically how many input and output pins does a module have. Okay, there's pointers to the wires. There's a pointer to the processing function, and so forth. So that's all the common information that's shared by all the modules. And you can think of this is doing object-oriented programming in C. So this is the base class, and this is the specific items for this particular type of module. Okay. So this all gets auto-generated. Okay. What we also generate in the C file now is we generate an object for the scalar class. So this is a small structure which essentially allows the module to be used by the framework. Okay. So there's pointers to functions, so it knows when I execute this module, what are the processing functions, bypass functions, and so forth. And it also knows how many words are in this module, how many public words, how many private words. So when it does memory allocation, it knows how much memory to allocate and so forth. Okay. And then inside the C code, there's also a processing function. So all the processing functions have the same basically form. They get a pointer to an instance. What you do then is you cast it to the correct type of instance. And then there are macros where you can say, hey, give me a pointer to the wires, all the wires that I have. Okay, tell me how many samples I have in my first wire. And then I call the processing function that does the actual work. Okay. And so the vex scale, you give it a pointer to the input data, a stride, a pointer to the output data, and a stride, what the gain to apply is, and how many samples to process. So this is the processing code that you have to write. Okay, and we've chosen to call these vector functions. What you could have done when you wrote the module, you could have just looped over and then done the scaling right here in the module. What we do instead is we jump off to these vector functions, and then we'll optimize the vector functions independently for each of the platforms. Okay. So that is what's happening inside the C code. Okay. We also generate module schema, and we'll look at that file, but it's basically a text, it's text information, and it gets compiled into the DLL. So for example, this does a translation between the server text syntax and the binary format. So when MATLAB sends a command, create a module scalar, okay, create an instance of this class of module. What the server tells the target is create a module with class ID boom. Okay, and so it essentially does the translation for us. And then when MATLAB says change the gain to 3.14, is it basically sends a command, set the variable with this object ID and this offset to 3.14. Okay, so that's really the translation table inside the server. So it's based on the schema information. So you never have to write this yourself. It's all auto-generated. But I just want to make sure you know all the pieces of information. Okay. Now, if you're on a embedded processor, there's basically a pound define called list of class objects, which are pointers to those class structures. And whichever modules you include here get added to the target and get compiled in. So when you're updating your list of modules on the target, you would update this pound define. And you saw that we have tools that will generate this pound define for you. Okay. So that's how it works on an embedded processor. You just reference the module and then it becomes available. Okay. And you can pretty much imagine what's happening now on the target. When I send the command, create the module with this class ID, down on the target, we walk through the list of objects and say, do you have this class ID? Do you have this class ID? Here's the class ID. Let me call your constructor function. And then it does the dynamic instantiation. Okay. And so that's kind of an overview. A bunch of fine points is all in the documentation. But in MATLAB, you can talk about module arguments. Remember how we have the arguments tab? They're treated a little bit differently. Okay, different types of variables, variable ranges, dealing with array variables and allocating memory for those. Okay, you can also have MATLAB set functions. So when we have a filter, you have a set function which will take, for example, your cutoff frequency and turn it into filter coefficients. And so you can have a version of that that runs in MATLAB that gets called when you're in design mode. And then you can also, there's also a version of that that runs down on the target as well. That's written in C code. Okay, so a bunch of fine points. Let's go ahead and just dive through. I'll show you some of these files in more detail, and you'll see how the pieces fit together. Okay, modules. And so there's an examples module folder. So to develop modules, you need the Pro version, and then you get the custom module SDK. And inside the custom module SDK, it comes with this examples folder. So we look pretty closely at the MATLAB part of it. Let's just look at those header files a little bit more. So here's the mod scalar example. Okay, and so we looked at this first part. Okay, So this is all auto-generated. We have that scalar instance descriptor here. And then it'll also make definitions for functions and so forth that get called and so forth. So that's the header file. Okay. Let's look at the source file here. Mod scalar example. Okay. All this initial part is auto-generated. And then this is the processing function. And this processing function, this is the part that you would manually write. And then everything else would be auto-generated for you. Okay. So you just got to write the small part of the code there. And this one shows you, it's kind of looping over, doing the processing here. And let me show you some of the vector functions. You can kind of appreciate what's happening behind the scenes. Okay, so this is our vector library. So for each one, there's generic code. So this is just standard C code. So if we look at the vex scale, okay, this is what it looks like. Nothing special here. You just loop over, you do the work, you advance by a source stride and a destination stride. So this is generic C code. I'll show you the generic C code for a biquad filter. Vec biquad. Again, it's a special code if it's a first order biquad, and this is your standard, I think direct form 2 biquad here. Okay, so you have your 5 multiplies and so forth. So we're just looping over fairly standard code. So when we write a module, we essentially start with this. And we say, okay, we're going to write the generic C code, make sure that it's working. And now, suppose we're working on a Cortex M4 processor. Well, we want that biquad to go faster. So we'll write specialized biquad code for the Cortex M4, which now does a whole bunch of loop unrolling, okay, so that we can get additional speed here from the M4 processor. Okay. Suppose you're running on an ARM Cortex-A. Let's look what the biquad looks like, vec biquad. Okay. So now we have kind of neon optimization for the biquad filter itself. So this allows it to go execute a lot faster than the generic C code. And suppose you're running on a Shark DSP. Okay, so the Shark is kind of best programmed in assembly, and this is what the Shark code looks like. Okay. And here's the inner loop for the Shark code. We have 1, 2, 3, 4, 5 instructions. And the Shark has like 0 overhead loop. And so the biquad executes in 5 cycles on the Shark. So we basically go all out optimization for the different processor families to make sure that all the primitives are running efficiently. Okay. So that's kind of the custom modules in a nutshell. And yeah.
Question. I searched my PC. I got lost. Where can I see those functions on my PC?
The vector functions?
Those files, the repository.
Yeah. So this is kind of our internal repository, and I don't know if you have the modules. Do you have the examples module folder? You may not have the custom module SDK. So
Yeah.
we may have to provide that for you if you need to write modules.
Do I have default module folder like this?
No.
I don't.
No. So we have standard version, pro version, and then to the pro version, you can add the custom module SDK. Yep. And so again, most customers are just using the standard version, pro version. Not that many need to write their own modules. Okay. So if you guys need to write modules, let us know. We can provide you with stuff.